Good day to you from Chem Help ASAP. This video provides practice problems on identifying whether an organic molecule is aromatic and then determining how many electrons are involved in the aromaticity. The video description contains links to printable copies of these problems and their solutions. Furthermore, links during the video will connect you to other videos that provide more detail on the material in the video. Determining aromaticity of a molecule involves Huckel's rules, or more properly, Huckel's rules. On the screen is my version of Huckel's rules. First, the molecule needs to have a ring. Second, that ring needs to be flat. We'll come back to this one. Third, each atom in the ring needs to have a p orbital. We'll come back to this one too. Fourth, the number of electrons in the p orbitals in the ring, when set equal to this equation, 4n plus 2, must solve for n with a value of 0, 1, 2, etc. Integer values. This is such a verbose item, so let's simplify it as much as possible. In practice, the number of electrons needs to be 2, 6, 10, 14, etc. That's the number of electrons in your p orbitals. Let's come back to these flat and p orbital rules. In general, these two rules together are almost always satisfied by having each atom in the ring be sp2 hybridized. In other words, if you have ring atoms that are not sp2 hybridized, then the ring will not be aromatic. There are exceptions, but they are very rare and strange. If each atom is sp2 hybridized, then each atom can be flat, which helps the ring be flat, and each atom will have an unhybridized p orbital. Note that in order to determine whether a ring is aromatic, you must be very comfortable with determining the hybridization of atoms. If you cannot correctly assign hybridization, then assigning aromaticity will be a struggle. Here are some quick tips for handling ring atoms. Atoms in an aromatic ring will fall into 3 categories, with each category determining how many electrons that atom contributes to the 4m plus 2 calculation. If the p orbital, and here is our p orbital, on an sp2 hybridized atom with 3 hybrids in the trigonal plane of the atom. If the p orbital is part of a pi bond in the ring, then the atom contributes 1 electron. Most people would say that the pi bond contributes 2 electrons, 1 from each atom in the bond. If the p orbital holds a lone pair, and that's supposed to be lone, lone pair. If the p orbital holds a lone pair, then the atom contributes 2 electrons. In rare cases, a p orbital can be empty, vacant. In those cases, the atom contributes 0 electrons towards aromaticity. These are the 3 options: 1, 2, or 0 electrons. If an atom has multiple lone pairs, you cannot count more than one of them toward the 4m plus 2 electron count. The key p orbital on an atom that lines up with the other p orbitals in the ring can hold at most 2 electrons. That is the upper limit. All right, let's see some examples. Here is our first problem. This molecule is called pyrimidine, and you might recognize that as one of the nucleobases that you find in DNA and RNA. So, pyrimidine, is this aromatic? Well, our first question is, do we have a ring? Yes, we do, absolutely. Is this ring flat? Now, I know to really answer this when you talk about hybridization, but in general, if you have a 5 or 6 membered ring, even maybe even a little bit bigger, these are going to tend to be flat. It's never a question of it'd be aromatic if it could be flat. Almost never is a question. So flat it's one of our questions, but it's rarely a deciding factor. Now let's go to p orbitals. Does every atom have a p orbital? The real question here is every atom in the ring sp2 hybridized. So these carbons that are part of a double bond, they are absolutely going to be sp2 hybridized. These nitrogens as well, they're part of a double bond, they are sp2 hybridized. So all of our atoms are indeed sp2 hybridized. And now the real question is, how many electrons do we have in our pi system? Well, this double bond right here, that's going to contribute 2 electrons. That's 1 electron from this carbon that's part of the double bond, 1 electron from that one. Same goes for this double bond right here. We're going to get 2 electrons. And this other double bond up in the upper right, that is also 2 electrons. Now the only kind of weird thing is here, what are we going to do about these nitrogen lone pairs? Like, do we count those or not? So if you look at this particular nitrogen, it is sp2 hybridized, and it has an unhybridized p orbital, and that p orbital is making a double bond. That means that p orbital is not holding that lone pair of electrons. And the same is going to be true for this nitrogen lone pair. That is not in a p orbital, because the p orbital is busy making this pi bond. Therefore, in this case, we ignore the lone pairs. And this is almost always the hardest part about doing these questions. What do I do with the lone pairs? Do I count them or not? In this case, we don't. So we have 6 electrons. 6 electrons solves out for our 4n plus 2. We solve n equals 1. That is a valid solution. And therefore, yes, this is aromatic, and our number of electrons in our pi system is 6 electrons. So that took a little longer, but that's how we'll work through each of these problems. Okay, problem number 2. Here we have a molecule. It has a ring, so at least we satisfied that criterion. Is it flat? Well, like I said, flat is normally not an issue, so we'll assume it's going to be flat as we move forward. Now, does every atom have a p orbital? So these 2 carbons in the ring, those are sp2 hybridized. Those are sp2 hybridized. Now, how about this oxygen? Let's complete the oxygen by giving it its lone pairs. Now, normally you look at an oxygen like this, and if this were, say, water, you would say, that's an sp3 hybridized oxygen. But that would assume that each lone pair wants a hybrid orbital. Lone pairs do not need to have hybrid orbitals, especially when they're next to double bonds. Lone pairs, when they're next to double bonds, tend to, one of them will want to go in a p orbital so it can delocalize and do resonance with the pi bonds. So this is actually, indeed, an sp2 hybridized oxygen. So everybody is sp2 here. Now let's count up our electrons. We have a double bond. That's going to be 2 electrons, and so we're counting 1 electron from each member of the double bond. That gives us 2. Here's another double bond to the right. That's 2. And one of these lone pairs, and only one of these lone pairs, can sit in the p orbital on this sp2 hybridized oxygen. And so we can get 2 electrons from that oxygen. And again, we can't count both of those lone pairs. We are not allowed to, because only one of those lone pairs can fit into that p orbital on that oxygen. And that gives us 6 electrons. So therefore, and that, let's go through the equation. If we set that equal to 4n plus 2, we will solve for n. Whoops, we're not going to solve for 4. We'll solve for n, and that gives us n equals 1, and it's a valid solution. So yes, this is aromatic, and it has 6 electrons in its aromatic ring. Now, something that's distracting is if maybe you can work through this problem and there's no issue, but then if someone point blank says, well, how about this nitrogen? That nitrogen is not part of the aromatic system. Is this really an aromatic molecule? Yes, it is. This aromatic ring makes the molecule aromatic. That doesn't mean there aren't pieces off the molecule that aren't part of the aromaticity. But if the molecule contains an aromatic ring, it's an aromatic molecule. It just has substituents that aren't part of the aromaticity. And this nitrogen lone pair, really, it's irrelevant. It's not in a ring atom, so who cares? That doesn't matter. That could be a methyl group, a nitrogen. It could be an isopropyl group. Doesn't matter. So yes, this is an aromatic molecule, and it has 6 electrons counting towards aromaticity. All right, this is a very interesting molecule. So first question, do we have a ring? Of course we have a ring. There is a nice six-membered ring there. Is it flat? Yeah, it's going to be flat. Okay, that's not a major question. Now, is every atom sp2 hybridized? Well, yes, they are. These alkene carbons, they're all going to be sp2 hybridized. This carbon with the carbonyl, that's going to be sp2 hybridized. And this nitrogen can be sp2 hybridized as long as we say that that lone pair is willing to go into a p orbital. We can make this nitrogen sp2 hybridized, and that lone pair would, because it's next to double bonds, and so that's not an issue. So everything is sp2 hybridized. So everything's looking good. Now let's just count up our electrons. That double bond is 2. That double bond is 2. We know that this lone pair is going to be included because it's in that p orbital. And then we run into this. What do we do with this carbonyl? So you could say, there are a couple ways to look at this. You could say that this carbonyl, this carbon is part of a double bond. Therefore, this carbon is going to contribute 1 electron towards aromaticity. Now, if we left it at that, then what we'd find is our number of electrons is 7. And if we try to put that into Huckel's rules, we'll find that n does not equal to 0, 1, or 2. I'm not going to do the math in my head, but it comes down to some non-integer value. So therefore, this would not be aromatic. And the fact is, this is correct. It's not an aromatic structure, and it's because the electron count is off, and it's because when you have double bonds coming off of a ring, this disrupts the aromaticity. So this, this looks like a tragedy. This molecule is so close to being aromatic. Well, this molecule has kind of a bright story. If we consider resonance for this molecule, you would say that that lone pair can make a new CN pi bond, and that will break that CO pi bond. And that'll get us to this structure. Let me draw in all these lone pairs. Minus, we'll have an N. That will now be plus, double bond there, there, and there. Well, now if we went through Huckel's rules, we would find that this ring is indeed aromatic. So we said no, the structure as drawn is not aromatic, but look, it has a resonance form that is aromatic. And if we counted up the electrons, we get 6 electrons. And that would give a solution down here, N equals 1. So it is possible that when you have a molecule, as drawn, it may not be aromatic, but then we look at a resonance form, and maybe it is aromatic. Likewise, maybe the original molecule is aromatic and the resonance form is not. And so this can greatly affect how you weigh which is the major contributor by looking at your resonance forms, and sometimes they're aromatic and sometimes they're not. And that can affect which one you think is the major contributor. So that's problem 3. Technically speaking, this question, as drawn, this is not an aromatic structure. Here is problem 4. Problem 4 is interesting as well. So we can see we have benzene rings in this molecule. So regardless of anything else we do, this is an aromatic molecule. At least parts of it are aromatic. Now a question is can we not isolate these 6-membered rings and think of them as a source of aromaticity? And can we instead think of the entire perimeter as its own ring? So that's the real question here. Is this molecule aromatic? Well, absolutely, it's aromatic. The question is, how big are we going to be able to think about this ring? And can we include other sites and not just isolate it down to a benzene ring? So do we have a ring? Well, we think so. We have this really big ring. This would be, how many atoms? There's 6 plus 6 plus 1. That's 13 atoms in our ring, actually. Now, how about, are they flat? Well, it's going to be, if we can get it aromatic, it'll certainly be flat. Now, does every atom have a p orbital? Absolutely. Each one of these carbons is sp2 hybridized. Each one of those is sp2 hybridized. Now, how about this carbon? This is a CH, and to have a negative charge, it's going to have a lone pair. We can put that lone pair in a p orbital, so that carbon as well can be sp2 hybridized. So everybody can have a p orbital. Now it's a matter of counting up electrons. We have 2, 4, we have 6, 2, 4, 6. That's 12, and this lone pair will also be in a p orbital. So that'll be 2 more. So that's 14 electrons. 14 electrons, if we put this through our equation, 4m plus 2, this solves out to say n equals 3. That's an integral value. Bam, this is an aromatic structure. So yes, it's aromatic, and it's aromatic as a system with 14 electrons. This structure has a special name. It's an anion, and yes, anions and cations can also be aromatic. And this is called a fluorenyl anion. And it is a special aromatic anion that you encounter with some frequency in organic chemistry. Okay, problem number 5. Just looking at this, we see a benzene ring. This is going to be an aromatic structure. But like the previous question, can we break away from just a 6-membered ring and count a larger ring size to say the entire thing is aromatic? That's the real question here. So definitely we're going to have an aromatic structure. So do we have a ring? Yes, we have, hopefully, this larger ring. So yes, we have a ring. Is it flat? It's going to be flat. Does every atom have a p orbital? Are they all sp2 hybridized? Of course, all these carbons, we've seen them multiple times in previous questions. Those are going to be sp2 hybridized. This carbon is sp2 hybridized. This nitrogen's part of a double bond. It will be sp2 hybridized. And this nitrogen, with its lone pair, we can put the lone pair in a p orbital, and it can also be sp2 hybridized. So, yes, everything is sp2 hybridized. Now let's start counting electrons. And let's not forget, we have this nitrogen lone pair up in the upper right. So we have 2 electrons in that pi bond. Each of these carbons contributes 1. So there's 2 in the double bond, 2 there, 2 there. We have 2 here, and we can also count the lone pair. So that's going to be 2 because that lone pair is in a p orbital. Now the question is, how about those electrons right there? Those electrons right there, we can't count them. This nitrogen has a p orbital. That p orbital is involved in making that pi bond. Therefore, it is not involved holding that lone pair. That lone pair is in an sp2 hybrid. So therefore, we ignore that lone pair, and that gives us 2, 4, 6, 8, 10 electrons. Whoops, having a hard time writing that. 10 electrons. And we put that into 4n plus 2. And n will solve out to be 2, and that's an allowed solution. So yes, this is aromatic. Well, we knew that when we saw the structure. Furthermore, it's aromatic with a full 10 electrons. Oh boy, this is a great example. Okay, so here we have a molecule. We obviously have a ring. That's a non-issue. Is it flat? Sure, it can be flat. Now, does every atom have a p orbital? These carbons are all sp2 hybridized. This oxygen, let's draw in the lone pairs. As long as we put one lone pair in a p orbital, we're fine. And we can only put one lone pair in a p orbital. So that can be sp2. How about this carbon? That is not sp2 hybridized. It's not. It has 2 hydrogens on it. That is an sp3 hybridized carbon. Nothing we can do about it. Every atom does not have a p orbital. This is not an aromatic structure. Now, we had a previous example where we said it's not aromatic, but then we drew a resonance form. So it would be really common. I'm going to redraw the structure down here. It would be very common for students to write something like this. And they would say, oh yeah, we can draw a resonance form here, and we can just do this. And that looks really nice. And that would be an aromatic structure. The problem is if you don't recognize there are 2 hydrogens here. And therefore, you can't do that resonance, because what you're going to do is you're going to put 5 bonds on this carbon. That is not an allowed resonance form, because you're exceeding the octet of this carbon right here. So this will not work. So even though we don't always draw the hydrogens on our carbons, you can't forget that they're there, because if you forget they're there, you're going to do crazy stuff like this and move electrons where you can't for resonance forms. Regardless, to answer the question, no, this molecule is not aromatic, and we can't draw aromatic resonance forms of it either. Okay, problem number 7. Here we have a ring. That's satisfied. Will it be flat? Sure. Does every atom have p orbital? Are they all? Can we make them all sp2 hybridized? Yes, yes, yes. And this nitrogen, it does have a lone pair, but it's part of a double bond. Yes, that will also be sp2 hybridized. Now let's just count up our electrons. Well, the double bond on the left will give us 2, and the double bond on the right will give us 2. And now what do we do with this lone pair? If we count it, we can make this aromatic. Problem is, we can't count it. This nitrogen has one p orbital that is lined up with the other p orbitals, and that p orbital is making a pi bond, and therefore that p orbital cannot hold that lone pair. That lone pair is in a hybrid orbital. Therefore, we can't count it. In total, we only have 4 electrons, and if we put that into 4m plus 2, we get, what do we get? Is that a 1.5? No, that's n equals 0.5, which is not an integral number. That is not a solution. Therefore, no, this is not an aromatic ring. Okay, problem number 8. Problem number 8 has a ring. We're off to a good start. Is it flat? Rarely an issue. We'll just say yes and move on. Now, does every atom have a p orbital? Well, these carbons will all be sp2 hybridized because they're all part of a double bond. This oxygen, it has a couple lone pairs. One of these lone pairs can go into a p orbital. In fact, it would prefer to, because that allows it to delocalize into the pi system. So that's not an issue. That oxygen can be sp2 hybridized. The same is going to be true for this nitrogen down here. That lone pair can go into a p orbital. Okay, so everybody has a lone pair. I'm sorry, not a lone pair, has a p orbital. Now, how many electrons do we have? And this is always a hard part. We know we have 2 double bonds, so that's going to be 4. We just said that this nitrogen has a p orbital, and we're going to put the lone pair in there. So we got to count those because those are in a p orbital. This oxygen, we also said one of these lone pairs is going to go into the p orbital. So that's going to be 2. And that means the other lone pair can't. We can only count 2 electrons. So that's going to give us 8 electrons. That will not give us a valid solution for 4m plus 2. What is that? N equals 1.5. That's not going to work. So no, this is not an aromatic structure. Okay, problem number 9. Now we have this kind of bigger ring, and the question is, what can we do with this bigger ring? So we have, do we have a big ring? Yes, we do. Is it flat? Sure. Does every atom in the ring have a p orbital? Well, all these carbons are good. This oxygen, we could say one of those lone pairs is in a p orbital and the other would not be, so that's fine. These carbons, however, those both have 2 hydrogens. Those are sp3 hybridized carbons. Those are going to prevent this larger ring from being aromatic. So this is not a larger aromatic ring. However, we do still have a benzene ring here. So this will be aromatic. And so when we reduce the discussion to just this ring, yes, every atom in that ring is sp2 hybridized. All those carbons are sp2 hybridized. And our total number of electrons will be 2, 4, 6. And of course, now that we've taken this part of the molecule out of consideration, it doesn't matter what those oxygen lone pairs are doing. So we're down to 6 electrons, 4m plus 2, n equals 1, and that looks good. So yes, this is an aromatic structure with a 6-electron pi system. Does not include this additional part of the molecule, but just this part of the molecule alone, if it's aromatic, means the entire molecule is an aromatic structure. Last structure, number 10. Here is our ring. So no problem. We do have a ring. Is it flat? Well, we'll find out. If it's aromatic, it'll certainly flatten out. Does every atom have a p orbital? In other words, is every atom potentially sp2 hybridized? All these carbons with the double bonds, There's no question. Now we have this weird thing. We have a carbocation down here. So this carbon is going to have a hydrogen, and it's going to have potentially a vacant p orbital here. And I say it's vacant because doesn't have a lone pair there. If it had a lone pair, it would be an anion. This is a carbocation. It has a vacant p orbital. But the key thing is it does have a p orbital. So all the atoms are sp2 hybridized, the atoms in the ring. Okay, what's our electron count? Well, we have 2 electrons from that pi bond, 2 from there, 2 from there, and a big 0 from the carbon, well, that is the carbocation. So that gives us 6 electrons, and that solves very nicely for 4n plus 2, n equals 1. Yes, this is aromatic, and we have 6 electrons in our aromatic system. This is a special carbocation. This is called a tropylium ion. And why is tropylium such a special carbocation? Well, it's special because it's especially stable. And why is it especially stable? Well, it's because it is indeed aromatic, and it has a longer lifetime than most carbocations you would see in a typical reaction. So that is our last question. I hope you enjoyed these problems and that they help you better understand how to determine whether a structure is aromatic and the number of electrons involved in the aromaticity. Please subscribe to the channel, like this video, or leave a comment. Thank you for watching. Remember that links to these problem sets are in the video description. Take care.